Yes, so welcome along to this session. So I'm going to be talking really about kind of big computers, big data, and really then how does that apply to Erlang and trying to bring the two together there. So first of all, something about myself. So I'm a platform architect, and I many years at Sun really helped whilst there. I really helped design the original kind of .com systems we put out at that time. Very large-scale systems in those days, as we powered up most of the big .com sites. That kind of some of that evolved into the big grid clusters we were building, and I personally did a cluster around that time of over 1,000 servers. Huge challenges in doing that in terms of the network connecting those together. I went on to Microsoft and was a principal DevOps architect there, really on their whole internet-facing side of the business. So what is now known as Azure, but also had Passport, Xbox Live, all those properties there. While I was there, we were adding something like 4,000 servers a month into the data center. So massive challenge there in how we could build those, how we could manage those. The other interesting thing there was it was very obvious that nobody knew how to write a cloud app in those days. People were developing an app, maybe running it with 6 or 7 servers. Maybe they had a SQL Server back end. They'd come to us and say, right, this works fine on 6 servers. Can you now give us 500? And their kind of expectation was it would miraculously just work and scale on these. And really, we set about at that time, really within Microsoft, looking at, well, how do we write an application which actually scales horizontally? Because nobody really knew. I've probably spent most of the last 10 years working in banks on high-frequency trading systems, and that's partly because that's been really interesting technology, and that's been pushing technology the hardest. But there's a certain amount of scale and things we've been doing there as well in terms of running large computers there. I've been involved in a couple of cloud startups, and that's really where a lot of my Erlang work has been, and that's really kind of what I'm going to lean towards in these discussions. So really, I guess it was probably when Intel kind of really stopped delivering us faster processors and gave us more cores that it really became apparent to us all that we were going to have to write concurrent programs. And I was writing things in Java and those in those days, and it was just too hard. And the thought of trying to write programs with hundreds, thousands of threads and debug them and get them to work really led me to start to look elsewhere and led me down the functional path. And I probably would have gone Haskell had it not been for the whole OTP side on Erlang, and that's really what pushed me towards there. As a platform architect, I've spent far too long of my lifetime building the basic infrastructure to run things, and just to find that it was all there and did the basics actually made a huge difference to me. So I started on my Erlang journey, and like with most things, it starts good, and then you start to hit some of the problems. You know, what's wrong with hyphens, guys? You know, the amount of people who must get caught on using a hyphen in a module name. Why isn't it documented anywhere? And why doesn't it give a decent error message? It's silly stuff. And of course, some of the other bits are difficult to get used to. You know, the immutable variables. You know, having to been forced to do recursion because there's no while and those kind of things. And OTP was good on paper, but it was so difficult to use. Of course, slow maths and things like that for chattiness and things dying because they're out of memory. So as is usual, you start all excited and then you hit all the problems. Thank you, guys. You saved my life. We do need more books on OTP. I know Francesco's one's out soon. That should help, but certainly that helps. And really kind of what I'm going to be talking on is really how we evolve Erlang now, how we leverage some of these other things. So let's kind of talk about big clusters and big data. So really what we talk about there are computers that fill a room. So if we look at kind of state of the art at the moment, so there's a continual race to build the biggest computer. If you go on to www.top500.org, you'll see the top 500 computers in the world. They get listed there. There's an annual bake-off where they run a benchmark and see what position you are in that ranking. And these are primarily used to do kind of the big science challenges, the global warming, weather forecasting, finding the elusive Higgs boson. So really a whole range of things there, but also things like web search. So I was building massive clusters at Microsoft, 20,000 servers to do search. So real big systems there. Picture on the right there is the Blue Gene computer at Lawrence Livermore. So it fills the room, and that's really what you got to think about on these things is that they do fill a room. There's kind of 3 generations of those. I'm going to be talking about those. So distributed resource managers, MPI, and then MapReduce, which is kind of where all the excitement's around now, and that's kind of that whole area is what people really talk about as being big data. And the first 2 were more about computing. The third one is more about handling large amounts of data, and that's really the focus on that there. I think all 3 methods are still viable and are still used, and I'll be talking more about those. So what kind of caused it in the first place? A lot of it was just, until then, people had brought very expensive big mainframe style computers, or they were the Cray XPs, but really there was dissatisfaction with the cost of those, plus they couldn't get any bigger, and people started to connect together lots of low-cost commodity computers. The original ones used distributed resource managers. We then got on to what known as MPI grids. Those then evolved with specialized hardware into vector grids. And then finally, we've got this whole kind of MapReduce area, the big data with Hadoop. So I'm going to drill into each of these boxes in a bit more detail. So if we look at distributed resource managers, this was really about submitting jobs. So you'd define a job, you'd submit it into something which managed a queue. A scheduler would then take it from that queue when the right resources were available. It would dispatch that onto some worker nodes. When they'd finished executing, their results would come back. The jobs in those days, and still today, are really not really much more than shell scripts. They partition the data manually. They typically use NFS to actually share data between those nodes. So relatively straightforward, but this was how a lot of the compute is done. Still carried on today. So examples are Condor, SunGrid NGM, Platform, TIBCO Data Synapse. They're all examples of distributed resource managers. The next phase around that evolution was really the message passing interface, and it really became a programmatic way in which these jobs could intercommunicate with one another. The basic scripts on the DRM really couldn't communicate. This gave an asynchronous message API so that those nodes could communicate. They could do things like rendezvous, they could share data. They added things like multicast to give efficient broadcasting of information. They evolved from NFS to cluster-based file systems, so much higher performance, allowed much greater data transfer rates between the systems, so you could now transfer gigabytes, terabytes of data into those systems. The top 500 rating is done using a Limpac benchmark, and that's actually run under MPI. It's actually a Fortran benchmark. So you'll see that this supports C and Fortran, the APIs for this. The benchmark itself does a lot of array manipulation. So it's very much focused towards that. If you look at the sensitivity of MPI performance, so this chart shows a number of different benchmarks down the side here. Along the bottom are different MPI implementations, and then along the top here are different network latencies, so the internode latency. And really what this shows is that when there's the performance drop in throughput of that cluster as you start to add network latency between those nodes. And that's something which is really important for these large clusters, that the throughput is very dependent on the network. The single instruction multiple data is really a way of using specialized hardware to execute the same program on different slices of the data. It's been used in GPUs for some time, and really what happened was people saw that they could leverage that same commodity hardware to actually execute their programs as well. So people started to actually program using the graphics primitives. That was difficult and messy. And NVIDIA commercialized a set of APIs known as CUDA. It's a C-level API, and it allowed people then to program that directly. Other hardware vendors, ATI, later acquired by AMD, did something similar. There was industry standardization around these APIs known as OpenCL. And then finally, Intel came out with their own a solution, which known as Phi. So these really provide large numbers of vectors, and that's primarily what these are used for. If you look at a typical CUDA server, so these are the kind of things we would deploy. So this is a 2U server. It has on it 2 Intel x86 processors here. You would then plug 4 of these Teslas, so 2 each side, into this system. Each of these Teslas has 512 cores. So when you combine the system together, we end up with 20 x86 cores and over 2,000 Tesla cores. If you build a rack of those, you've got 41,000 cores in a single rack. So a lot of compute power. Programming model is much more complex, though. This is really what we talk about hybrid computing. So you have your main program running on the system over here, and you've got your SIMD architecture running on these GPU cores. And part of the challenge when building these computers is trying to determine the right balance between how many x86 cores do I need for to keep the workload busy on effectively these vector cores. If you look at a program example, you can see that a lot of what it's doing is executing on the main program. It then has to transfer the data across to the CUDA engine. Once it's done that, it loads the code across. The same code runs on every core. So each core is running a different slice of that data, but they're all running in the same code with their own threads. So you end up with lots and lots of these threads. You start the program, you wait until that's finished, and you copy it back again. Many times you find that because of the overhead in transferring across, it's often quicker just to execute something locally than it is to transfer it across. So all the time you're trying to determine, do I run locally? Do I take the hit and transfer across? So again, that's one of the big challenges in this space is trying to decide what to run locally, what to transfer across. And because Intel are putting more and more cores on the local side, you can easily end up with 20 or 30 cores running on the x86 side, maybe 200 odd vector engines now. They keep adding more and more there. So you can end up with a lot of vector engines locally as well. So what were the top 10? So this was the last positioning, last November. The top 10 computers. China's got the biggest one at the moment, so you can see that's Intel Xeons with Intel Phi's running alongside that. There's a Cray running AMD x86. That's got NVIDIA. You've got you've got an IBM Power. You've got a Spark, another IBM Power, another x86 here. One thing you'll notice here as well is that none of them run Ethernet. They all either run custom interconnects or they run InfiniBand. You don't get into the top 20 now running Ethernet. It's a theme which I'll mention as well. It's really, we've kind of hit the scalability wall on Ethernet. We've hit the scalability wall on TCPIP, and so these guys have already made the move. If we look at that number one computer, so it's the Tian in China. So it's 3 million cores in that one computer, giving 33 petaflops of compute power. So massive compute power. But when building these, and I was involved with several of them, often what would happen is somebody would come to us and say, well, my budget is X. What position in the table can you buy me or can you deliver me for that amount of money? And we'd end up working with a lot of people who would, everybody would bid, and whoever got them highest up the table would be who they placed the order with. The other constraint we often found was people would say, well, I've got 10 megawatts in my data center. That's all I can have. How much power can you give me? How much compute power can you give me for my 10 megawatt capacity? And we'd go through great exercises trying to do the trade-offs here, trying to design the maximum either for the money or for the power rating we could get there. The software is designed to cope with failure, so you avoid any single points of failure in that software, but you build it with commodity servers. And really what you find is that once your software can survive failures, you're better to take cost out of those servers and put more servers in, and accept the fact that a bigger amount will fail. So 98% of 1,500 servers is better than 99.9% of 1,000 servers, and that's we would see making small savings on the servers, leaving quite small things off meant we could put a lot more in. The whole network design is a challenge. Once you've got more servers and you can plug into a single Ethernet switch, it becomes really challenging designing the network, and a lot of work goes on in that area. We see a lot of performance impact on that. Often we would find that to get the same amount of throughput, we'd have to put a much higher number of servers on than if we were able to lower the latency on the network. We could get away with a much smaller number of servers. So, unfortunately, it's a complex area. And if anybody wants to know much more about the network, come and see me later. It's an area I've done a huge amount of work on, but we don't have time to cover that in too much detail today. So some of the applications which go on there, I've done a lot of work in the financial services space on things like option pricing, market valuations, value at risk, but there's all these other big science stuff which goes on these as well. Now let's go across to MapReduce. So this was really popularized in a paper published by Google. And really, MapReduce is really about taking a large chunk of data, partitioning that across, executing that in parallel, combining those results back again, the reduction, and then iterating around that if need be. That you'd go through another mapping, another reduction. The original paper really only describes the mapping. So you've got a key. You've got a map of a key and a value, and you from that you produce a list with another key and another value, and that's really the mapping function. And then you apply a reduction function on that. So you've got another key value, and you create a list of those, and you combine those lists together. So the paper doesn't really describe any real implementation. It really only describes the mapping and reduction at this function level. However, they did attract a lot of attention, and Doug Cutting, who was at that time search director of the Internet Archive, had built his own search indexer for the Internet Archive known as Nudge. And really, what he saw when he looked at the Google papers of MapReduce and Google File System, which is a cluster file system, he saw that the layered approach they were taking to engineering was going to be a much more reliable way than the monolithic solution he'd built with Nudge. So he actually reverse engineered both Google File System and MapReduce, implemented them in Java, and then added his internet search on top of that. In 2006, he joined Yahoo, and they'd all similarly been impressed by Google's papers and effectively backed him to make that an open source project, gave him the resources to do that, and really as a result of that, the Apache Hadoop project was created. They kept Nudge internally, so it was really only the basic infrastructure which went into Hadoop. Initially, only really scaled to 20 servers, but Yahoo put a lot of effort in over the years. They created a big research grid internally for that. So in 2011, they were reported as having 42,000 nodes running on Hadoop, hundreds of petabytes of data there. So using it for search. Now, Yahoo pulled out a search, and I've loaded it all to Bing now, and I would probably say Facebook are now probably the largest Hadoop user now. in 2012, they were reported to be over 100 petabytes, growing at about half a petabyte a day. The important thing is, that people get confused about, is Google actually don't use Hadoop. They have their own MapReduce implementation, which is totally internal. They don't. That's not open source. That's all written in C++. So Hadoop is reverse engineered MapReduce. It's not Google code. Hadoop is actually much more of an ecosystem rather than just a single piece of software. You've got a cluster file system, the Hadoop file system, which takes the data, it replicates it across multiple nodes, by default 3 copies, and makes that available to every node within the cluster. There's a columnar database as well, known as HBase. That's part of that. You've then got all the MapReduce processing side, the cluster management. Then there's a whole host of data access components, and then really the workflow and the management side of that. Hadoop itself, though, is written in Java, and really only contains really basic get, set, and scan primitives. You really can't do a huge amount with it. You've got to write pretty complex Java programs to actually make use of that. And really, what's happened over the last few years is, I would say, most of the energy has gone around query engine work. And that's really what people think about with Hadoop now, is using some of these query engines which are available in the community. So Hive was the original one, which was a SQL-like. I would say the one which is probably getting the most attention at the moment is Presto. That is full ANSI SQL. That's come out of Facebook. They use that enormously. They've got thousands and thousands of people in Facebook who are running Presto. So huge amount of effort and resources going into that. You've got Impala, and you've got another reverse engineered Google one. So Dremel is reverse engineered implementation of Google's BigQuery API. So again, they're custom query engine, but it's a reverse implementation of that. Lots of Hadoop clones out there. So you can take the original. There are other people who add value to it and add other things. Sometimes they're based on the open source code. Other times they're completely reverse engineered themselves. So you've got IBM and Intel doing things there particularly. There's a lot of derivative projects as well. Apache Shark is one. One of the things we found about Hadoop jobs is it's optimized for big data for taking a long period of time. So think minutes, hours, days, weeks for a typical Hadoop job. If you want something done in seconds, it's not a good environment. It takes a long time to start up. It takes a long time to get your data there. Between each MapReduce cycle, it actually writes to disk. So it actually saves it to disk, and the next side picks it up again. So there's a lot of disk I/O activity going on between all these steps. Some of the derivative projects, such as Shark, and in fact there's a Spark as well goes with that, are much more aimed at shorter term, more interactive kind of use cases where you want to send a query and get a response back in around 20 seconds. So a much smaller data set to execute on. So a lot of work going on in those in recent years. So I would say when people talk about Hadoop nowadays, they probably mean the query languages. And utilizing those to actually query large data sets. They're running on top of a Hadoop infrastructure cluster, but what people are interacting with are the actual query languages themselves, although they weren't actually part of the original Hadoop system. So if we go back now and look at where we have with these grids, we can see we've got distributed resource managers, we've got MPI grids, we've got these matrix calculations of vector-intensive workloads, and we've got kind of the big data and the analytics with Hadoop. But what do we do with distributed applications? What do we do with cloud scalability? How do we build the next Facebook? You know, a billion users, and I can't run it on Hadoop, and I can't run it on these SMD grids. They're not the right things. To me, that's a real interesting challenge. Is how do we build the next Facebook? And of course, I think we should use Erlang and OTP, and I'm sure lots of you do. But and of course, you know, it's scalable. We can spawn. You can build clusters really easily. OTP's got a lot of the basics in there, so that really helps us build reliable systems. And I think so Erlang and OTP together solve the difficult parts for us of getting concurrency built into your programs and doing the reliability. But you know, Erlang cluster scalability is limited. We've got due to chattiness. OTP supervision trees are really just designed to work on local nodes. When you look at the distributed application controller, you find it's all about reliability. It's all about letting you pick from other nodes to run on. Similarly, Gen server cluster behavior, where it allows you to have a single service runnable on multiple nodes. So you know, my feeling was, well, surely somebody must have solved this somewhere. I started to look around, found a computer, so that was like a dynamic resource manager, but no commits to that. Node Finder's a neat little piece of code, so it allows you to use multicast to discover nodes in a cluster, saves you adding them manually. There's even a separate version for AWS because there's no multicast support on AWS. Disco project looks quite interesting, so that's done out at Nokia Research in Palo Alto. They're running on an 800 core cluster there. That's much more around a distributed resource manager. They've got their own distributed file system in there. Bit of the dependency on Python baked in there, but some interesting stuff there. React Core, of course, that pulled out by the Basho guys from React and made separately available. So there's some useful things there in terms of Node Watcher to do your cluster membership. You can even advertise different kinds of services there. It is implementing the master worker pattern using vnodes. So when it talks about vnodes, various workers. Allows you to maintain global state in the ring by gossiping there, so it's got that built in. It allows you to send workload to different nodes to different vnodes based on hashing. Basho have done a good job at trying to make it generic, but it's still very much got a very strong React bias into it. So it's kind of part of the way there, but there's still it's still a challenge to use that for more generic things. The whole release project looks really interesting. I'm looking forward to finding out more about that here. I know Simon's got a session tomorrow on that. So EU-funded program. I think the goal of 100,000 cores is a bit modest, given that the biggest computer in the world is already at 3 million. But it's a start. There's a lot of interesting papers. I'm looking forward to actually finding out what we can access and download. I think the whole S group side looks really interesting in terms of being able to partition the cluster better. There's not a lot of software available yet. I'm hoping that's going to increase on there. But it's certainly a promising move in the right direction. I think there's a lot of people looking to solve these problems now. So in conclusion there, so I think Erlang OTP really help solve the most difficult part. So that's writing scalable code that can run reliably. There's no doubt that is the much more difficult thing. So I think Erlang and OTP gets us there. But there's a lot which needs to be done to help that scale. Some of the work we do in the large clusters, we use technologies like RDMA to overcome the TCPIP bottleneck. That would be a great technology to actually embed inside Erlang to get some of the scalability there. Be good to see things like multicast used to reduce chattiness. Again, that's a standard cluster technology to use. These are all solutions to known problems we ought to be leveraging. So, and I think the real opportunity now for Erlang and OTP is really to take this next step and become the premier cloud platform. There's too many of us out there doing this ourselves, solving the problem the hard way. It's I think if we can do it as a community, then we really do start to get to massive scale on this. Okay, with that, we'll take any questions.
Thank you. So if you have any questions, I will walk to you so that you can say your question and the camera will get it.
Yeah, you mentioned a little bit about like where, yeah, or the typical thing is maybe where Erlang reaches the computation bottleneck, but I wonder what is the state for Erlang when we come to the data bottleneck, like moving data around and so on. I'm thinking about next generation.
Well, that's right. That's right. So that's where I think we get hit by the TCP/IP bottleneck. You know, we have to copy everything at the moment. And that means the TCP/IP it becomes a fundamental bottleneck in moving that data around. So that's where technologies such as RDMA could actually help there immensely.
But it's the network that will be the bottleneck rather than Erlang, right?
On the modern compute clusters, the network is faster than the computers. The network isn't the bottleneck; it's the computers are the bottleneck. But you have to get TCP out the way before you get to that point.
Any other questions?
In your opinion, what is like the low-hanging fruit in terms of Erlang tooling that Erlang is currently lacking, and like what should be delivered first in order to, you know, like improve either cluster management or Erlang distribution?
I think simple things like being able to spawn a job to run on the least loaded node in a cluster. So that kind of thing. You know, they're all problems which everybody's writing their own code to solve, and it's silly that there's 50 of us writing our own code to solve the same problem. That's a really trivial thing. I think things like RDMA are more complicated. That requires a lot of building. But tools like Node Manager are a good help in terms of it helps form a cluster without you having to go off and ping every node yourself.
Don't you think that this should be part of OTP?
Yeah, absolutely, absolutely. And it, you know, OTP is kind of almost there, isn't it? You know, it teases you by letting you put node in there.
Okay. Are there like some different languages or frameworks which can be used as a, you know, learning point to, you know, copy some of the best practices or solutions?
Well, I think some of the practices we can copy. So that's where things like using multicast to share information. So multicast allows one-to-many publication. So one person can push out its state saying, this is how busy I am at the moment. Everybody can receive that without having to send a message to every other node in the cluster. So we use it a lot in large clusters to broadcast cluster state. You can use that information then to determine, for example, which is the least loaded node, which one's got available resources that I could spawn the next job onto it. Because all these things are trying to get balance, is trying to, how do I do it without adding too much overhead in itself? Otherwise it can be more, can cost more to determine where to run the job than it does to run the job itself. So it's trying to get the balance right there.
Yeah, first great talk. Wholeheartedly agree. But one thing you didn't touch on, I would guess with your experience building large internet properties for Microsoft, security must have come up. So I just wondered if you had any, just thoughts framed by the whole discussion around security in the state currently with Erlang OTP.
So yeah, primarily. We'd be running, certainly where I've been running OTP, we've been running it behind the firewall. Been using DMZ there and running it behind the firewall. And that's probably true for most of the cluster state, that we have an access layer and access into that. I probably wouldn't want to run internal OTP protocols across the internet. And that's probably true for most of the clusters. It would tend to use, have separate clusters at different locations, and then communicate with them at a higher level. I've done a lot of work there with RabbitMQ, using that to interconnect different clusters together across the internet. That I think is probably the safer. You really got to have kind of a high performant, low latency internal network. You want to use for OTP, because you need that reliability. You've got to have a very reliable network there to run something like OTP on top of it. You've got to have no single point of failure. You want all those characteristics. I really can't guarantee that once you go across onto the internet, but I can have reliable clusters dotted around the internet, and I can have them sharing state between them, and that's the kind of approach I've been leaning towards.
A question on the Erlang node as a concept. So one Erlang Cloud environment could be that I deploy an Erlang node, and as I add processes to that node spreads across several more hardware nodes seamlessly. Another way, if that's not possible, maybe one should have the Erlang node as something that runs on one hardware entity, and maybe could migrate away. Maybe it's deployed automatically on the least loaded and so on. But which one of those paths do you think is more viable?
I think they're both viable. I don't think there's a right or wrong way to do this. I mean, once you get a reasonable number of nodes in the system, you've got to cater for that. Some of them will die. You've constantly got this scenario of nodes appearing and nodes disappearing, and you're having to write the software to cater for that scenario, and that's fairly challenging in terms of doing that. But once you've done that, you've then got a very scalable system.
But should we have a Erlang Cloud environment where we behind the scenes replicate the Erlang nodes so that they will never fail, or should you as a programmer know that my Erlang nodes will potentially fail, so therefore I have to cope with it on the application layer?
So the way we've done that elsewhere is that you do it on each job, so that the job gets run on a node. If that job fails, then something has to rerun that somewhere else, and that tends to be the approach which has been used there. Now that's a bit different to a standard supervisor model, and there's going to be cases where you need that constant service running, and then the supervisor's got to be able to restart it on another node. If it sees that it's failed on this node, it's got to be able to restart that on another node. So you know, there's different compute patterns there which we've got to cater for. Some are job intensive, some are service intensive. So I think we need to cater for both.
Well, we have time for just one more question before we go to the next.
Hi. Is distributed hash table will help OTP to scale?
Sorry, is
distributed hash table?
It's
like all the peer-to-peer protocol and so on.
So React Core kind of gives you a means to try to scale that. So you know, they use the ring cluster there to do that, and I leverage a lot of technologies. I use Amnesia a lot. That helps to deliver some of that global state, but you've kind of got some scalability constraints on that. So there's no one right answer. I think that's the key thing, that we need a number of different OTP and infrastructure building blocks to help build these scalable applications.
Thank you.
Thank you.
Thank you everyone for a very interesting